This is a combined presentation of chapters 17 and 18. Chapter 17 is Introduction to Semiconductors and Power Supplies. And chapter 18 is Tubes, Transistors, and Amplifiers. To begin, chapter 17. Some of the objectives for the chapter are to define electronics, explain the doping process, explain how N-type and P-type materials are made, discuss how N-type and P-type materials conduct electrical energy, explain forward and reverse biasing, discuss various types of semiconductor diodes, explain the operation of half-wave and full-wave rectifiers, explain power supply filtering, explain power supply load characteristics, outline various methods for regulating voltage, discuss methods for raising voltages, and construct simple power supplies. Some of the keywords encountered are anode, bridge rectifier, cathode, diode, doping, electronics, forward biased, full wave rectifier, half wave rectifier, hole, N-type, P-type, pentavalent, percentage of voltage regulation, potential barrier, potential hill, rectification, reversed biased, ripple, and trivalent. Electronics defined as the study of how the electrons in active devices such as integrated circuits, transistors, and vacuum tubes. A timeline showing the development of these three generations of electronic devices is shown in figure 17-1. Again, electronics can be defined as the study of the flow of electrons in active devices such as integrated circuits, transistors, and vacuum tubes. During the experiments in the 1800s, 1883 to be specific, with the incandescent lamp, Thomas Edison noticed that electrons could be driven off the hot filament of a lamp. He called this the Edison effect. In 1904, J.A. Fleming built a diode, a two-element vacuum tube that changed AC to DC. Changing an alternating current to a direct current is called rectification. That same year, Lee DeForest invented the first vacuum tube amplifier. It was called a triode. This material will be discussed in detail later in this chapter. The first solid-state amplifier device was called the transistor. It was invented at Bell Laboratories in 1948. The technology used in transistors was key to the development of the third generation device, the integrated circuit, sometimes called the IC. While it may seem that there have been more and more advances in electronics technology in the past few years, all recent advances are still based on the integrated circuit. The integrated circuitry, including the microchip, continues to get smaller and smaller, but the basic principles remain the same. In the next three chapters, you will cover the three generations of electronic devices, the concepts, vacuum tubes, transistors, and integrated circuits will not be covered in chronological order. These systems will be presented in an order that will enhance your comprehension and mastery of this subject. The simple diode will be discussed first, followed by power supplies. These are the first systems encountered in almost every electronic system. Next, the vacuum tube will be introduced, followed by the transistor and amplifier. The vacuum tube and transistor are presented together because they work on similar principles. The last concept in the series will be the integrated circuit. Integrated circuits are based on transistor technology. Your understanding of electronic systems will be greatly expanded upon completing these next three units. Those units again are 17, 18, which are here included in this presentation, and 19, which will be the next presentation. 17.1 Semiconductors. The study of semiconductors, transistors, and integrated circuits (ICs) requires an understanding of new concepts in electronic theory. Let's review what we have learned about conductors in Chapter 1. 1. First is that copper and several other metals such as silver and gold make good conductors. Second, certain materials such as glass and rubber are insulators. Third, semiconductors are composed of materials that are neither good conductors nor bad insulator or bad conductors or good insulators. Again, semiconductors are composed of materials that are neither good conductors nor good insulators. Semiconductor diodes, transistors, and integrated circuits are all made of semiconductors. Their materials are neither good conductors nor good insulators. However, the ability of these devices to conduct electricity or to insulate can be greatly enhanced. It will be necessary to take a deeper look at the atomic structure of materials to fully grasp the theory of semiconductor operation. Atomic characteristics. Diagrams of the atomic structures of silicon, Si, and germanium, Ge, are shown in figure 17-2 on your screen. Silicon is in great supply. It makes up to 28% of the world's surface. The atomic number of silicon is 14. The atomic number of germanium is 32. Recall that the atomic number is the number of protons or electrons that make up an atom of an element. Therefore, silicon has 14 electrons in its orbit. Germanium has 32 electrons in its orbit. Note that both silicon and germanium have 4 electrons in their outer orbits or in their outer rings. These electrons on the outer rings are called valence electrons. In some atoms, valence electrons are able to bond with the valence electrons of another atom. This is called a covalent bond. The atoms are each bonded to their own nucleus and to each other. This bond creates a lattice crystalline structure. Germanium and silicon both lend themselves to this type of bond. Figure 17- shows a silicon structure. It is a pure insulator. It will not conduct electricity. Conduction of electricity. Electrical current is best defined as the flow of electrons in a conductor. The flow of electrons results in energy. An example of this action is shown in figure 17-4, that's the bottom left of your screen. An electron is added to one end of the conductor, another electron leaves at the opposite end. This chain reaction is the conduction of electricity by electrons. In figure 17-5, bottom right of your screen, an electron is removed from one end of the conductor. This action leaves a hole where there should be an electron, but there's not. Again, in the figure, an electron is removed from one end of the conductor, and this action leaves a hole where there should be an electron, but there's not. The hole is strongly attracted to another electron. The hole is positive. The next electron fills up the hole and leaves a positive hole in its place. Each positive hole is filled in turn by the next electron. When a vacant hole appears at the other end of the conductor, this chain reaction is conduction of electricity by holes. The study of semiconductors is concerned with conduction by electrons and by holes. Doping. Recall that pure silicon is a good insulator. Adding an impurity to the pure silicon changes the conduction traits of the material. The process of adding impurities to pure semiconductor material is called doping. The result of doping is an intrinsic semiconductor. Again, the result of doping is an intrinsic semiconductor. This means the material is not in its pure form. A pure semiconductor is intrinsic. Trivalent and pentavalent impurities are most often used for doping in transistors. Again, trivalent and pentavalent impurities are most often used for doping in transistors. Trivalent impurities have 3 valence electrons. Pentavalent or pentavalent impurities have 5 valence electrons. Again, trivalent impurities have 3 valence electrons. Pentavalent impurities have 5 valence electrons. Figure 17-6, top of the screen, is a chart showing the quantity of valence electrons in several materials. Adding doping elements to semiconductor materials results in either an excess or shortage of electrons in the covalent bond. Again, adding doping elements to semiconductor material results in either an excess or shortage of electrons in the covalent bond. For example, arsenic, which is a pentavalent, 5 electrons in its outer shell, is added to silicon. 4 valence electrons of arsenic form a covalent bond with the 4 valence electrons of silicon. 1 electron from the arsenic remains free. Figure 17-7, bottom of your screen. The arsenic donated a free electron to the structure. All pentavalent impurities donate free electrons, and they are called donor impurities. In this structure, electricity is conducted by negative electrons. Therefore, the crystal becomes an N-type crystal. What occurs when a trivalent impurity or trivalent impurity is added to a pure semiconductor material? It has only 3 electrons to join into a covalent bond. 1 more electron is needed to complete the lattice structure. A hole remains in place of the missing electron, figure 17-8. This hole will accept an electron. A trivalent impurity then is called an acceptor impurity. In this structure, electricity is conducted by positive holes. The crystal becomes a P-type crystal. Figure 17-9, top of the screen, shows conduction through an N-type crystal. 17-10, bottom, shows conduction through a P-type crystal. Notice that the hole moves in the opposite direction of the electron flow. Review questions for Section 17.1, define electronics. It is the study of flow of electrons through devices such as integrated circuits. Electrons on the outer ring of an atom are called valence electrons. What is a covalent bond? It is a bond of valence electrons between two or more atoms. Doping is the process of adding impurities to pure semiconductor material. It results in an intrinsic or extrinsic semiconductor, and it changes the conduction traits of a pure material. Pentavalent, pentavalent impurities are known as donor impurities, and they produce N-type crystals. Trivalent impurities are known as acceptor impurities, and they produce P-type crystals. Seventeen point two, semiconductor diodes. A diode is a device designed to permit electron flow in one direction and block flow from the other direction. A diode consists of two electrodes, a cathode and an anode. A cathode is the electrode or an electrode that emits or gives off electrons. An anode collects the electrons and puts them to use. A semiconductor diode is the result of fusion between a small N-type crystal and a P-type crystal, figure 11-11, 17-11 up top. At the junction of the two crystals, the carriers, electrons and holes, tend to diffuse. Some electrons move across the barrier to join holes. Some holes move across the barrier to join electrons. Remember that unlike charges attract each other. Due to this diffusion, a small voltage or potential exists between the regions near the junction. How does this happen? The region of the P crystal near the junction becomes negative. It has taken electrons from the N crystal. The region of the N crystal near the junction becomes positive. It has lost some electrons, but it gained holes. This voltage or potential is called a potential hill or a potential barrier. The barrier prevents the other electrons and holes in the crystal from joining. The symbol for a semiconductor diode is shown in 17-12. The arrow side of the symbol denotes the anode portion of the diode. The anode contains the P-type material. The bar side of the symbol denotes the cathode portion of the diode. The cathode contains the N-type material. Forward and reverse biasing. A voltage potential is connected across a diode in figure 17-13. The positive terminal of the core of the source is connected to the P crystal. The negative source is connected to the N crystal. The negative electrons in the N crystal move toward the barrier. The positive holes in the P crystal move toward the barrier. The source voltage opposes the potential barrier and reduces its barrier effect. This allows the electrons and holes to join at the barrier. Therefore, current flows in the circuit. It flows in the P crystal by holes. It flows in the N crystal by electrons. The diode is biased in a forward direction or forward biased. There is a minimum forward bias voltage, Again, there's a minimum forward biased voltage needed to overcome the potential barrier for current to flow in the circuit. This minimum voltage depends on the type of semiconductor material used. It requires approximately zero point 0.6 volts of potential to forward bias in a silicon diode. Types of semiconductor diodes. Diodes are used for a number of purposes: voltage rectification, voltage regulation, and even light production. Those are some of their various uses. Following is a brief description of some diode types you might encounter. Point contact diodes. The point contact diode is used for detection and rectification. It consists of a small piece of N-type germanium crystal. Against this crystal is pressed a fine phosphor bronze wire. While the diode is being made, a high current is run through the diode from wire to crystal. This forms a P-type region around the contact point in the germanium crystal. The point contact diode therefore has both the P and N-type crystals. Its operation is like that of a junction diode. Silicon rectifiers. Diodes conduct current more easily in one direction than in another. This process is used to produce rectification. A key semiconductor diode is the silicon rectifier. Figure 17-15 shows two typical rectifiers. However, silicon rectifiers come in a wide variety of shapes and sizes. Figure 17-16 shows some common diode outlines. Silicon rectifiers have high forward and reverse current ratios. This is the ratio of current allowed in the forward direction compared to the current allowed in the reverse direction. They can achieve rectification efficiencies of greater than 99%. These rectifiers are very small, light, and built to last a long time. In addition, they can be made resistant to shock and mishandling. Silicon rectifiers do not decay with age like a vacuum tube rectifier does. Zener diodes. An electronic device that can be used as a voltage regulator is the Zener diode, figure 17-17. Figure 17-18 shows a characteristic curve for a Zener diode. When the diode is forward biased, it acts like a diode or a closed switch. However, the Zener has unique reverse bias qualities that make it differ from the typical voltages. Diode. Again, the Zener has unique reverse bias qualities that make it differ from the typical diode. The Zener will go on to reverse bias at various voltages. The amount of voltage required for reverse bias varies according to the Zener diode selected. Some typical reverse bias voltages are 2.4, 5.1, 6, and 9.1, and 12 volts. At this point, when the applied voltage is increased, the forward current increases. This small reverse current flows until the diode reaches the Zener breakdown point, V2, in figure 17-18. At the Zener breakdown point, the Zener diode is able to maintain a fairly constant voltage as the current varies over a certain range. Because of this attribute, the diodes provide excellent voltage regulation. Figure 17-9 shows a Zener diode being used as a simple shunt regulator. Light emitting diodes. The light emitting diodes LED is a special function diode. When connected in the forward bias direction, it emits light. Figure 17-20. Light emitting diodes are made from semiconductor compounds such as gallium arsenide, gallium arsenide phosphide, and gallium phosphide. All LED receives energy from a DC power supply or a battery. This causes the electrons and holes to combine in the p-n junction region of the diode. This combination creates photons, which are particles of light that can be seen. Each photon is produced from one hole, positive charge, and one electron, negative charge. Different LED colors are achieved by using different materials in the manufacture of the LED. Figure 17-21. This figure shows the operating principle of an LED. The LED must be connected to a power source with some form of resistance in series with the LED. If the LED is connected directly to a source with forward bias, the LED will be destroyed. Biasing diagrams for some common LEDs are shown in figure 17-22. Note that the cathode lead is the shortest lead, that is the negative. It is also the closest to the notch on certain diodes. LEDs have many uses. For example, they are used on the instrument panel of cars, clocks, watches, and many other electric devices. Diode characteristics and ratings. Ratings of diodes and rectifiers are commonly based on current and voltage capabilities and peak inverse voltage. The peak inverse voltage, or PIV, rating used by manufacturers defines the greatest reverse voltage that can be applied across a rectifier without damaging it. An example of this: 1 amp at 50 PIV for a 1N400I or 1N401, a 1N4001 silicon rectifier. This means that a 1N4001 silicon rectifier has to withstand, or can withstand, a maximum applied reverse voltage of 50 volts. Many diodes are identified by a 1N. Examples of this are the 1N4001, 1N5400. Some manufacturers use their own labels, such as the HEP 320, SK3051, or the 276-1102. Series and parallel rectifier arrangements. Diodes or rectifiers can be connected in series or parallel. This connection is made to improve the voltage or current capabilities of a single rectifier. Connecting diodes in series increases voltage ratings over the value of a single rectifier. Diodes can be connected in parallel to improve the current handling ability of the combination over that of only one diode. Again, diodes can be connected in parallel to improve the current handling ability of the combination over that of only one diode. Care must be used when connecting diodes in a series or parallel arrangement. The electrical characteristics must match exactly, otherwise the current or voltage drop will not be exactly equal across both diodes, even when the diodes have the same part number. Testing diodes. You have learned that diodes with a forward bias direction have a low resistance to current. A reverse bias direction has a high resistance or high resistance. This allows diodes to be tested using an ohm meter. To test a diode in the forward bias direction, connect the diode across the ohm meter. Set the range switch on the low resistance setting, times 1 or times 10. The reading should be low. A low reading is from 50 to 1000 ohms. See figure 17-23, part A. To test a diode in the reverse bias direction, connect the diode across the ohm meter leads. Set the range switch to a high resistance setting such as times 10K or times 100K or times 1 mega. A good diode will show a very high resistance. See figure 17-23b. Many new digital meters have a diode test function built in. The model with a diode symbol on the selector switch is shown in figure 17-24. A properly connected diode can be tested by turning the switch to the diode function. Review questions for section 17.2. 1. A diode is a device that will pass current in one direction and block it in the other direction. 2. What occurrence prevents electrons and holes in a crystal from joining? That would be a potential hill or barrier. 3. Draw and label the symbol for a semiconductor diode and an LED. And you can see those on the screen. Question 4. In reverse bias, the source voltage aids the potential barrier and resists electron flow. In forward bias, the source voltage opposes the potential barrier and allows electron flow. Question 5. How much potential is required to forward bias a silicon diode and a germanium diode? That would be 0.6 volt for silicon and 0.2 volts for germanium. Question 6. Look up a 1N4003 diode in a parts catalog and determine the current rating and PIV rating. And I will leave this question for my audience to answer. Number 7. A Zener diode is an electronic device that acts as a, or an, fill in the blank, that would be a voltage regulator. Question 8. A particle of light is called a photon. (17.3) Power supplies. The proper operation of electronic equipment requires a number of source voltages. Low DC voltages are needed to operate ICs or integrated circuits and transistors. High voltages are needed to operate the CRT or other devices. Batteries can provide all of these voltages. However, electricity from electrical and electronic devices are commonly supplied by the local power company. This power comes out of an outlet at 115 volts AC with a frequency of 60 Hz in the United States. Different voltages are needed to operate some equipment. A power supply is an electronic circuit designed to provide various AC and DC voltages for equipment operation. Some of the power supply functions, top of the screen. The complete power supply circuit can perform these functions. Step voltages up or step voltages down by transformer action to the required AC line voltage. Provide some method of voltage division to meet equipment needs. Change AC voltage to pulsating DC voltage by either half wave or full wave rectification. Filter pulsating DC voltage to a pure DC steady voltage for equipment use. And finally, regulate power supply outputs in proportion to the applied load. A block diagram illustrating these functions is shown in figure 17-25. Note that certain functions is not found in every power supply. Figure 17-26 is a typical commercial power supply. Power transformers. The first device in a power supply is the transformer. Its purpose is to step up or step down alternating current or alternating source voltage to values needed for radio, TV, computer, or other electronic circuit use. For this, review the transformer action in Chapter 12. Most transformers do not have any electrical connection between the secondary and primary windings. See figure 17-27. This means that the transformer isolates the circuit connected to the primary from the circuit connected in the secondary. Isolation, as defined in Chapter 12, is a term that means that there are no electrical connections between the primary and the secondary on the transformer. An isolation transformer is a transformer that has the specific purpose of isolating the primary circuit from the secondary circuit. Using an isolation transformer is a safety feature because it helps prevent shocks in the secondary. Our body and hands must be joined across both leads of the secondary connections in order to receive a shock. The safety condition described above does not hold true in the primary with commercial AC provided by the power company. One connection is hot, which means that the connection is electrically energized. The other is grounded or neutral. Standing on the ground while touching the hot connection will result in a shock. Again, this is for the AC primary. Touching the ground connection alone will not result in a shock. Secondary windings can be tapped to provide different voltages. A tap is placed midway between the two ends of a secondary winding and is called a center tap. Again, a tap is placed midway between the two ends of a secondary winding is called a center tap. Many power supplies use a center tap secondary transformer winding. The tapped voltages seen on the screen are 180 degrees out of phase with respect to the center tap. A variety of transformers can be found in nearly all electronic devices. You should understand the basic theory and purpose of the transformer. For this, review Chapter 12 again if necessary. A lesson in safety. Transformers produce high voltages that can be dangerous. Proper respect and extreme caution must be used at all times when working with or measuring high voltages. Half wave and full wave rectification. After a voltage has gone through a power supply's transformer, the next step is rectification. The process of changing an alternating current to a pulsating direct current is called rectification. When changing an AC signal to DC, there are two types of rectification: half-wave rectification and full-wave rectification. With the half-wave rectification, only half of the input signal passes on through the rectifier. With the full-wave rectifier, the entire input wave is passed through. Half-wave rectification. In the figure you see on the screen, the output of a transformer is connected to a diode and a load resistor that are in series. The input voltage to the transformer appears as a sine wave. The polarity of the wave reverses as at the frequency of the applied voltage. The output voltage of the transformer's secondary also appears as a sine wave. The magnitude of the wave depends on the turns ratio of the transformer. The output is 180 degrees out of phase with the primary. The top of the transformer at point A is joined to the diode anode. Note that the B side of the transformer is connected to ground. During the first half cycle, point A is positive. The diode conducts, producing a voltage drop across resistor R equal to IR. During the second half cycle, point A is negative. The diode anode is also negative. No conduction takes place and no IR drop appears across R. An oscilloscope connected across R produces the wave form shown. It is shown to the right in figure 17-30. The output of this circuit consists of pulses of current flowing in only one direction and is at the same frequency as the input voltage. The output is a pulsating direct current. Only one half of the AC input wave is used to produce the output voltage. This type of rectifier is called a half-wave rectifier. Look at the polarity of the output voltage in figure 17-30. One end of the resistor R is connected to the ground or to ground. The current flows from ground to the cathode. This connection makes the end of R connected to the cathode positive, as shown in figure 17-29. A negative rectifier. A negative rectifier can be made by reversing the diode in the circuit, as seen in figure 17-31 on the screen. The diode conducts when the cathode becomes negative, causing the anode to become positive. The current through R would be from anode to ground, making the anode end of R negative and the ground end of R more positive. Voltages taken from across R, the outputs would be negative with respect to ground. This circuit is called an inverted diode. It is used when a negative supply voltage is required. It is possible to have a power supply that provides half-wave rectification without the use of a transformer. This circuit is not isolated. There is no step up or step down of current voltages. This circuit is a simpler, less costly design, and since there is no transformer, it can be used in smaller spaces. See figure 17-32. Full wave rectification. The pulsating direct voltage outputs of a half-wave rectifier can be filtered to a pure DC voltage. However, the half-wave rectifier uses only one half of the input AC wave. A better filtering action can be obtained by using two diodes. With this setup, both half cycles of the input wave can be used. Both half cycles at the output wave have the same polarity in this full wave rectifier. Figure 17-33 follows the first half cycle. Figure 17-34 follows the second half cycle. To produce this full wave rectification, a center tap is made on the secondary winding. This tap is attached to ground. In figure 17-33, point A is positive and diode anode D1 is positive. Electron flow is shown by the arrows. During the second half of the input cycle, point B is positive, diode D2 or diode anode D2 is positive, and current flows as shown in figure 17-34. No matter which diode is conducting, the current through load resistor R is always in the same direction. Both positive and negative half cycles of the input voltage cause current through R in the same direction. Again, both positive and negative half cycles of the input voltage cause current through R in the same direction. Output voltage of this full wave rectifier is taken from across R. It consists of direct current pulses at twice the frequency of input voltage. Figure 17-35 shows this. Again, output voltage of this full wave rectifier is taken from across R. It consists of direct current pulses at twice the frequency of input voltage. To produce this full wave rectification in this circuit, secondary voltage was cut in half by the center tap. The diodes D1 and D2 used in figures 17-33 from before and 17-34 from the prior figures are packaged both individually in pairs. Figure 17-36 shows a two rectifier package. The center lead is used as the connection for the cathodes. The cathodes are wired together. Bridge rectifiers. It is not always necessary to use a center tapped transformer for full wave rectification. Full secondary voltage can be rectified by using four diodes in a circuit called a bridge rectifier, figure 17-37 and 17-38. Two circuits are shown so that the current can be observed in each half cycle. In figure 17-37, point A of transformer secondary is positive. Current flows in the direction of the arrows. When point B is positive, current flows as in figure 17-38. Again, notice that the current through R is always in one direction. Both halves of the input voltage are rectified and the full voltage of the transformer is used. Filters. The outputs of either the half wave or full wave rectifier is a pulsating voltage. Before it can be applied to other circuits, the pulsations must be reduced. A steadier DC is needed. It can be obtained using a filter network. In figure 17-40, the E average, the line E average, shows the average voltage of the pulsating DC wave. It is equal to 0.637 times peak voltage. The shaded portion of the wave above the average line is equal in area to the shaded portion below the line. Movement above and below the average voltage is called the AC ripple. It is this ripple that requires filtering. The percentage of ripple as compared to the output voltage must be kept to a small value. The ripple percentage can be found using the formula. The formula is percentage of ripple equals to E RMS of ripple voltage divided by E average of total outputs, all times 100%. Capacitor filters. A capacitor connected across the rectifier output provides some filtering action. See figure 17-41 top. The capacitor is able to store electrons. When the diode or rectifier is conducting, the capacitor charges rapidly to near the peak voltage of the wave. It is limited only by the resistance of the rectifier and the reactance of the transformer windings. Between the pulsations in the wave, voltage from the rectifier drops. The capacitor then discharges through the resistance of the load. The capacitor, in effect, is a storage chamber for electrons. It stores electrons at peak voltage and then supplies electrons to the load when rectifier output is low. See figure 17-42. Capacitors used for this purpose are electrolytic types because large capacitances are needed in a limited space. Common values for the capacitors range from 4 to 2000 microfarads. Working voltages of capacitors should be in excess of the peak voltage from the rectifier. LC filters. The filtering action can be improved by adding a choke in series with the load. This LC filter circuit appears in figure 17-43. The filter choke consists of many turns of wire wound on a laminated iron core. Recall that inductance was that property of a circuit that resisted a change in current. A rise in current induced a counter EMF that opposed the rise. A decrease in current induced a counter EMF that opposed the decrease. As a result, the choke constantly opposes any change in current, yet it offers very little opposition to a direct current. Chokes used in radios have values from 8 to 30 henries. Current ratings range from 50 to 2000 milliamperes. Larger chokes can be used in transmitters and other electronic devices. Filtering action as a result of the filter choke is shown in figure 17-44, top of the screen. A second capacitor can be used in the filter section after the choke to provide more filter action. See figure 17-45 middle. Action of this capacitor is similar to the first capacitor. The circuit configuration appears as a Greek letter pi. The filter is called a pi section filter. When the first filtering component is a capacitor, The circuit is called a capacitor input filter. When the choke is the first filtering component, it is called a choke input filter. Figure 17-46. The choke input filter looks like an inverted L, so it is also called an L section filter. Several of these filter sections can be used in series to provide added filtering. In the capacitor input filter, the capacitor charges to the peak voltage. In the capacitor input filter, the capacitor charges to the peak voltage of the rectified wave. In the choke input, the charging current of the capacitor is limited by the choke. The capacitor does not charge the peak voltage. As a result, the output voltage of the power supply using the capacitor input filter is higher than the one using the choke input filter. Review questions for section 17.3. 1. Define the power supply. It is a device that provides various AC and DC voltages. 2. List 5 functions provided by a complete power supply. First is to step voltages up or down by transformer action. Second is to provide a method for voltage division. Third is to change AC voltage to pulsating DC voltage by half-wave or full-wave rectification. 4 is to filter pulsating DC voltage to a pure DC voltage. And 5th is to regulate power supply outputs in proportion to the applied load. Question 3. The first device in a power supply is the transformer. 4. A circuit that changes alternating current to a pulsating DC current is a rectifier circuit. 5. Name two types of full wave rectifiers. That is the center tap rectifier and the bridge rectifier. Number 6. What is voltage regulation? The output voltage of a power supply will usually decrease when the load is applied. This decrease is not good and needs to be minimized. The size of this decrease is measured in comparison to the no load voltage. The voltage decrease under the load compared to the power supply voltage with no load is called percentage of voltage regulation. It is one factor used to determine the quality of a power supply, expressed mathematically as the percentage of voltage regulation equals to ENL minus, or taken away, EFL divided by EFL times 100. That is the equation up top on your screen, where ENL equals voltage with no load and EFL equals voltage with full load. Load resistor. To complete the basic power supply circuit, a load resistor is connected across the supply, figure 17-47 on your screen. This resistor serves three important purposes. First, the load resistor serves as a bleeder. A bleeder allows charged capacitors to drain. During operation of a power supply, peak voltages are stored in the capacitors of the filter sections. These capacitors remain charged after the equipment is turned off. These capacitors can be dangerous if accidentally touched by a technician. The load resistor allows these capacitors to discharge when not in use. The wise technician will always take an added precaution and short capacitors to ground with an insulated screwdriver. Second, the load resistor improves regulation. The load resistor acts as a preload on the power supply. It causes a voltage drop when the equipment is attached to the supply. The added drop is fairly small and the regulation is improved. That is also a reason why the power supply draws energy constantly when connected. For example, assume the terminal voltage of a power supply is 30 volts with no load resistor. No equipment is connected. When the equipment is connected and turned on, the voltage drop is 25, or the voltage drops to 25 volts. Regulation is 20%. See the previous example under voltage regulation. If the resistor across the power supply produces an initial drop to 26 volts, the output voltage is considered 26 volts. If the equipment is now connected to the supply, causes the voltage drop to 25 volts, then the power supply regulation is as seen on the equation worked out. 26 volts minus 25 volts divided 25 volts times 100, which in this case gives us only 4%. So the usable voltage supply has only varied 4% instead of the 20 from the example, the prior example. A further advantage of preloading the supply is an increase in the choke filtering action. The resistor allows current to flow in the supply at all times. A choke has better filtering action under this current condition, and when current varies between a low value and zero. Again, a choke has better filtering action under this current condition than when current varies between a low value and zero. Third, the load resistor acts as a voltage divider. The load resistor provides a way of obtaining several voltages from the supply. Replacing the single load resistor with separate resistors in series provides several fixed DC voltages. Figure 17-48, a sliding tap resistor, can also be used to provide voltage adjustments. This circuit is called the voltage divider. It takes advantages of Ohm's law. The voltage drop across the resistor equals the current times resistance, or E equals to I times R. In figure 17-48, the previous figure, three resistors are equal. The voltage drop divides equally between them, and their sum equals the applied voltage. If other voltages are required, resistors with other values can be used. Do not neglect the effect of connecting the load or a load to one of the taps on a voltage divider. This load is in parallel to the voltage divider resistor. It decreases total resistance and therefore changes the voltage at that tap. Example, in part A in figure 17-49, the voltage divider consists of 3 kilo ohm resistors. The supply of 30 volts divides to 10 volts, 20 volts, and 30 volts at terminal C, B, and A, respectively. In part B, a load of 5 kilo ohms is connected to terminal C as shown. It is parallel with R3, and resistance becomes as shown on the screen, where RT equals to R3 times RL divided by R3 plus RL, which gives us 2500 ohms in this case. The total resistance across the power supply with RL connected is 5000 ohms plus 5000 ohms plus 2500 ohms, or 12,500 ohms. Now the current through the divider can be calculated as seen on the middle of the screen, left side, as I equals to E source divided R, and I equals in this case 30 volts divided 12,500 ohms, or 0.0024 amps, or 2.4 milliamps. Using the total current, we can calculate the individual voltage drops. The voltage at point C is EC equals to I times R, which equals to 0.0024 amps times 2500 ohms, which is 6 volts. So the voltage at point B is 18 volts. If another load were connected to point B, a further change of voltage division would result. Voltage regulator circuit. Some method of providing a constant voltage output at the power supply under varying load condition is needed. This method would take into consideration the effect or the fact that a voltage drop across a resistor is equal to the product of current and resistance. This method comes in the form of a circuit called voltage regulator. It is shown in figures 17-50 and 17-51. The total input of the power supply filter is applied to terminals A and B. Regulator output is across points C and B. The voltage regulator used in figure 17-50 is often called a 3-terminal fixed voltage regulator. A common output regulated voltage can be 5, 6, 8, 12, 15, 18, 24 volts, etc. Various current ratings are also available from manufacturers. Regulators come in a number of common transistor packages designs: TO3, TO39, TO202, TO220, etc. The solid-state regulators are basically blowout proof. They require that a heatsink be used to remove excess heat from the device. The external circuits used for these voltages or for these voltage regulators are quite complex. They have a number of transistors, diodes, Zener diodes, and resistors built into one small package. Figure 1751 shows 2 voltage regulator schematics and their package designs. An example of a use for a voltage regulator can be seen in an automobile. An automobile's voltage regulator controls the voltage level from the alternator. Review questions for section 17.4. A power supply has no load, or a power supply has a no load voltage of 65 volts. Voltage drops to 45 volts when a load is applied. What is the percentage of voltage regulation? For that, we use the formula given earlier. We plug in the values of 65 minus 45 divided by 45 times 100, which gives us a total of 44.4%. That is the percentage of voltage regulation in that case. Question 2. List 3 purposes for using a load resistor in a power supply. That is 1 for bleeding capacitors, 2 to improve voltage regulation, and 3 to divide voltages. Question 3. What is the purpose of a voltage regulator in a power supply? That is to provide a constant voltage under varying loads. (17.5) Voltage doublers. Up to this point, it has been assumed that the source of power was 117 volts AC, found in homes and schools. The transformer was used to step up or down the voltages required for the electronic circuits. Because transformers are heavy and costly, voltage multiplying circuits have been devised to raise voltages without the use of transformers. Study figure 17-2, 17-52. It shows the action in a half-wave voltage doubler circuit. In part A of figure 17-52, the input AC voltage is on the negative half cycle. As a result, point A is negative. Current flows from point A through the rectifier dP and charges capacitor C1 to the polarity shown. During the positive half cycle, point A is positive. The applied peak voltage is 165 volts, is in series with the charged capacitor C1. In the series connection, the voltages add together, so the output from the doubler is the applied voltage plus the voltage of C1. Current cannot flow through the rectifier D1 due to its one-sided conduction. The output waveform shows half-wave rectification with an amplitude of about twice the input voltage. The rectifier D2 permits current to flow in only one direction to the load. A full wave voltage doubler is drawn in figure 17-53. During the positive peak of the AC input, point A is positive. Current flows from point B, charging C1 in the polarity shown, through D1 to point A. During the negative cycle of the inputs, point A is negative. Current flows through D2 to C2, charging it to the noted polarity to point B. Notice that during one cycle of an AC input, capacitors C1 and C2 have been charged, so that the voltages across C1 and C2 are in series. The output is taken from across these capacitors in series. The output voltage is the sum of both voltages or twice the input voltage. Voltage doubler circuits provide useful high voltages for circuits needing low current. Because output voltage depends on charged capacitors, voltage regulation is poor. Conventional filter circuits are needed to smooth out the voltage as in transformer rectifier circuits. What type of circuit is shown below and how does it operate? That is the first question for the review questions, section 17.5. And that type of circuit is a full wave voltage doubler. Full wave voltage doubler. And to explain the operation, during the positive peak of the AC inputs, point B is positive. Current flows from point A, charging C2 in the polarity shown, through D2 to point B. During the negative cycle of the input, point B is negative and current flows through D1 to C1, charging it to the noted polarity to point A. Notice that during one cycle of AC input, capacitors C2 and C1 have been charged so that the voltages across C2 and C1 are in series. The output is taken from across these capacitors in series. The output voltage is the sum of both voltages or twice the input voltage. Voltage doubler circuits provide useful high voltages for circuits needing low current. But because output voltage depends on charged capacitors, voltage regulation is poor. So conventional filter circuits are added to smooth out the voltage as in transformer rectifier circuits. Question 2. A line voltage of 117 volts AC produces a peak voltage of 165 volts when using a voltage doubler. And that amount or value is given in the text for this section. Question 3. Why are voltage doubler circuits important for electronic equipment? And that is that they provide higher voltages when less amperage is required. Finally, the summary for this chapter. The three generations of electronic devices are vacuum tubes, semiconductor materials, and integrated circuits. Semiconductor materials or semiconductors are materials that fall between conductors and insulators in terms of resistance. Common materials used for semiconductors are silicon and germanium. Trivalent and pentavalent elements are added to pure silicon or germanium to make N-type or P-type semiconductors. The process of adding impurities is called doping. Rectification is the process of changing AC to DC. Diodes are PN semiconductor devices, which can be used as rectifiers. Reverse bias produces the effect of high resistance in a diode. Forward bias provides a low resistance path through the diode. Diodes are labeled with an 1N prefix. They are rated by peak inverse voltage, PIV, and maximum current rating. Diodes can be tested using an ohm meter or a diode tester on a digital meter. The light emitting diode or LED is a special function diode that produces light when connected in the forward bias mode. Light consists of photons. Photons are created by joining of electrons and holes in the PN junction. Power supplies are electronic circuits that provide various DC and AC voltages and currents for equipment. The basic circuits in many power supplies include transformers, rectifiers, filters, and voltage regulators. Transformers and voltage regulators are not found in all power supplies. The purpose of a transformer in a power supply can be to 1. Increase the voltage and decrease current. 2. Increase current and decrease voltage. 3. Provide isolation, and or 4. Provide two equal voltages, 180 degrees out of phase, using a center tap. A rectifier changes AC to DC or pulsating DC. Following are schematics of some important basic line and transformer operated rectifier circuits. Shown on the left is the single diode half wave output, the bridge rectifier full wave output, the single diode half wave outputs, the center tapped transformer full wave output, and the bridge rectifier full wave output. A power supply filter uses capacitors, inductors, and resistors to change pulsating DC to pure DC. The percentage of voltage regulation can be used to determine the quality of a power supply. A smaller percentage means a higher quality. A bleeder resistor is a resistor placed in parallel or shunt across the output of a power supply. It provides a load, a discharge path on which charged current can flow, and a limited amount of regulation of voltage. There are two basic types of voltage regulators, half wave and full wave. Both operate from the principle that capacitors, which always charge up to a peak value of a waveform, can be connected in series with each other, full wave, or with a line voltage, half wave, to provide an added voltage. Finally, test your knowledge. Questions. Number 1. A semiconductor is neither a good conductor nor a good insulator. 2. Define atomic number. It is the number of atoms or neutrons in the nucleus of an atom. Question 3. Electricity can be conducted in two ways. Name these ways. That is by the movements of electrons and by the movement of holes. Question 4. Explain the difference between donor impurities and acceptor impurities. Donor impurities have an extra electron for covalent bond, usually pentavalent. Acceptor impurities have an extra hole, a trivalent electron, outer orbit. Question 5. A diode consists of two electrodes. Name these. And that is the cathode that emits or gives off electrons, and the anode, which collects electrons and puts them to use. Question 6. A potential hill or barrier prevents electrons and holes from joining. Question 7. In forward bias, the barrier effect is opposed. In reverse bias, the barrier effect is aided. Question 8. A point contact crystal has B. A N-type crystals with a fused phosphor bronze wire for the P-type region. Number 9. What is PIV? That is peak reverse voltage, able to be applied to rectifier diode without damage. Or the peak reverse voltage is the max reverse voltage able to be applied to the rectifier diode without damage. That is what a PIV is. Question 10. Draw a label with a typical diode and label the anode, cathode, and the polarity markings. That was attempted to be shown there by the question number 10 on the left side of the screen. Question 11. A power supply provides various AC and DC voltages for equipment operation, can change AC voltage to pulsating DC voltage, and can filter pulsating DC voltage to a pure DC voltage. All of the above. Question 12. List in order the devices a current goes through in a power supply. That is the transformer, the rectifier diode or diode, the filter, the capacitor and the inductor, and finally the voltage regulator or capacitor. Question 13. A lack of electrical connection between the secondary and the primary windings is known as isolation. 14. In order to rectify both half cycles of the input wave, a central tap is made on the secondary winding. Question 15. What is the purpose of a filter network? And that is to smooth out the pulsating DC to a pure DC signal. Question 16. State the equation for finding the percentage of ripple. And that equation is percentage ripple equals to E RMS of ripple voltage divided by E average of total output voltage, and you multiply that by 100%. Question 17. Name two devices that can be used to improve filtering action. Those are capacitors and inductors. 18. Why is the output from a capacitor input filter higher than that of a choke input filter? That is because the charging and discharging effect Question 19. The terminal voltage of a power supply is 30 volts. When a load is applied, voltage drops to 28 volts. What is the percentage regulation? And that was attempted to be worked out with the formula E and D minus EFL divided by EFL times 100, and that ultimately gives us 7.14% or 7.14%. You can see the problem worked out under question 20. Question 21. What is the purpose of a voltage regulator circuit? That is to minimize the voltage drop when a load is introduced to a circuit. That is project 17-1. If you are interested in completing building this project, there it is. Project 17-2, building a trickle charger. Project 17-3, building a small power supply. Again, project 17-1 was building a voltage regulator. And this is a interlude, a sidebar for superconductivity. Superconductivity is a phenomenon in which certain metals, alloys, and ceramics conduct electricity without resistance. Superconductivity occurs in metals and alloys such as lead, mercury, and tin at temperatures near absolute zero, that is negative 460 degrees Fahrenheit or negative 273 degrees centigrade. Some ceramics become superconductors at temperatures as high as negative 234 degrees Fahrenheit, negative 148 degrees centigrade. In 1911, Heike Kamerlingh-Onnes discovered superconductivity while researching the effects of extremely cold temperatures on different metals. Onnes discovered that mercury lost all resistance to the flow of electricity when cooled to about 4 Kelvin. Before Onnes' discovery, there wasn't any way to eliminate resistance. Although copper, aluminum, silver, and gold are excellent conductors, there is a loss of some electrical energy because of resistance. The modern theory of superconductivity, the BCS theory, was developed by American physicists John Bardeen, Leon N. Cooper, and John Robert Schrieffer. According to the theory, a superconductor has no electrical resistance because of an attractive interaction between its electrons that results in the formation of pairs of electrons. These electrons pairs are bound to one another and flow without resistance around impurities and other imperfections. In an ordinary conductor, resistance occurs because its unbound electrons collide with imperfections and then scatter. Superconductivity is used in the field of electromagnetics. Powerful superconducting magnets use less electricity than ordinary magnets. These magnets are being used in many areas, including medicine, transportation, and the study of physics. In the medical field, magnetic resonance imaging, MRI, machines use superconducting electromagnets to generate a powerful magnetic field. MRI technology allows physicians to identify abnormalities without performing surgery and without exposing the patient to radiation. Maglev, or magnetically levitated trains, use superconducting electromagnetic coils. The coils are mounted on the bottom of the train, and aluminum coils or sheets are set in the guideway. When the trains move over the guideway, it induces a current. The guideway coils become electromagnets with the same polarity as the train coils, and the two types of coils then repel each other. The propulsion force is strong enough to raise the train. Superconducting magnets allow physics or physicists to build more efficient particle accelerators. The ring of superconducting magnets produces a magnetic field that keeps the particles in the vacuum chamber by bending their paths into circular orbits. The discovery of superconducting ceramic materials has made it possible to use superconductors in computers and other electronic devices. However, the discovery of a superconductor that could operate at room temperature would make it impossible to use superconductors in an indefinite or infinite, or would make it possible to use. However, the discovery of a superconductor that could operate at room temperature would make it possible to use superconductors in an infinite number of applications. One of the most practical would be the generation and transmission of electricity. Generators would be smaller and more efficient, and power lines would carry current from a fuel source over long distances without any loss of power. This is chapter 18, Tubes, Transistors, and Amplifiers. Objectives for the chapter are to explain the operation of a vacuum tube, describe the workings of a cathode ray tube, explain the operation of the bipolar transistor, explain the operation of field effect transistors, discuss different biasing techniques, identify various transistor circuit configurations, list the components of amplifier circuits and give the function for each component, explain amplifier operation, compute the gain of amplifier circuits, perform DC load line analysis on a transistor circuit, discuss the advantages and disadvantages of various methods of amplifier coupling, and finally to describe several common thyristors. Keywords of the chapter are amplifier, bipolar junction transistor or BJT, cathode ray tube, common base or CB, common collector or CC, common emitter or CE, cutoff, decibel, dB, field effect transistors, FET, FET, forward biased, junction field effect transistor or JFET, load line analysis, metal oxide semiconductor field effect transistor or MOSFET, NPN, PNP, quiescent point or Q point, reverse biased, saturation, thermal runaway, and finally thyristors. These terms will appear throughout the chapter. Pay close attention when those are brought up, since they won't be shown, not necessarily shown during the presentation. They will, however, be mentioned and defined within the text, so listen carefully for those. Vacuum tubes led the way to the development of many electronic devices, such as the radio receiver, radio transmitter, television, the radar, and the first computers. Most of the vacuum tube applications have now been replaced by the transistor. Transistor circuits can operate more quickly, are more sensitive to small currents, and allow for much cheaper and more compact designs. However, there are still applications, some in the music industry, where vacuum tubes can still be found. Many musicians still prefer the rich, mellow sounds produced by electronic tubes over those produced by transistor amplifiers. First, we look at the design of the electronic tube. When we will explore the transistor, then we will explore the transistor and the operation of common amplifier circuits. Lastly, we will look at two common thyristors. 18.1 Vacuum tubes. Vacuum tube use has been replaced in large part by the use of transistors and the integrated circuit, or IC. The vacuum tube still finds some special uses, such as in cathode ray tubes, CRTs, which are found in some, not most, but some remaining computer monitors. For the most part, however, vacuum tubes use more power, take up more space, and produce more heat than transistors and integrated circuits. The vacuum tube is a direct result of Thomas Edison's experiment with the incandescent lamp. In this experiment, a metal plate was placed in the vacuum bulb containing the filament. A battery and a series meter were connected between the light filament and the plate. At this point, Edison discovered that electric current would flow through the lights if the positive terminal of the battery was connected to the plate. However, if the negative battery or the negative battery terminal was connected to the plate, no current will flow. See figure 18-1. At that time, the electron theory was not yet discovered, and the flow of current through the light was a mystery. Today we understand electron theory. Certain metals and metal oxides give up free electrons when heated. The heat supplies enough energy to the electrons to cause them to break away from the forces holding them in orbit. They become free electrons. This process is known as thermionic emission. Again, this process is known as thermionic emission. In Edison's experiments, a cloud of free electrons emitted from the filament of the light bulb. Or in Edison's experiment, a cloud of free electrons was emitted from the filament of the light bulb. When a positive plate was placed in the bulb, the free electrons were attracted to the plate. Since unlike charges attract, a flow of electrons means that a current is present. The meter attached to the plate circuit showed that electrons were passing from filament to plate. The vacuum tube uses the same principles discovered in the laboratory of Thomas Edison. Thermionic emitters. Better emitting materials have been developed in the years since Edison's carbon filament. Many materials, when heated to the point of emission, will melt. For many years, tungsten seemed to be the best material. It required a great deal of heat for proper emission, yet it was strong and durable. Tungsten is still used in large high-power vacuum tubes. To lower the working temperatures and power usage, the thoriated tungsten emitter was developed. That was the thoriated tungsten emitter. It consisted of a thin layer of thorium placed on the tungsten emitter. Thorium is one of the heaviest metallic elements. Its symbol is Th and its atomic weight is 232.04. It is mined in Brazil, India, and South Africa. This type of emitter produces the proper emission at much lower temperatures than pure tungsten. The most efficient emitter is the oxide coated type. The emitter is a metal, such as nickel. On the emitter, a thin layer of barium or strontium oxide is formed. Because of its low power usage and high emission, this type of emitter was widely used in vacuum tubes for radios, televisions, and other electronic devices. Cathodes. The emitter in the vacuum tube is called the cathode. Heat can be supplied either directly or indirectly. Both methods have certain advantages. Schematic diagrams of both types of tube are shown in figure 18-2. Equipment that uses batteries for power. Again, equipment that uses batteries for power works best with directly heated cathodes. There is less heat loss, and the filament can be designed so that only a small amount of power is consumed during use. When an AC source is handy, the indirectly heated cathode is more powerful. There's little power loss, and the heater voltage source and cathode can be separated. This eliminates any humming in the circuit. Diodes. Recall that a diode consists of two electrodes. In the case of a vacuum tube diode, the two electrodes are the cathode and plate. Again, the cathode can be heated directly or indirectly. The plate is a round piece of metal that surrounds all elements in the tube. The plate acts as a collector of electrons emitted from the cathode. See figure 18-3. The heater connections are H1 and H2. These connections can be joined to an AC source. The first number in a tube name is the approximate voltage that should be applied to the heaters. For example, a 6H6 tube needs 6.3 volts. A 12AX7 needs 12.6 volts. And a 25Z6 needs 25 volts. When the tube in figure 18-3 is turned on, the heaters indirectly heat the cathode. This causes a thermionic emission of electrons. If the diode plate is joined to the positive terminal of the battery in the circuit, electrons will flow in the circuit from cathode to plate. If the connections are reversed, no electrons will flow. This electron tube acts as a one-way valve. It permits electrons to flow in one direction only. This is just like the semiconductor diode discussed in chapter 17. A certain temperature, or at a certain temperature, the cathode emits the largest number of electrons. These electrons form a charge around the cathode. The cathode has been made slightly positive because of the emission of electrons. Some of these electrons are attracted back to the cathode. When the plate is made positive, many electrons are attracted to it. This is electron flow. The plate can be made more positive by applying a higher voltage. A greater number of electrons are attracted, and there is an increase in current. Figure 18-4 shows the increase in current as a result of an increase in plate voltage. At some point, as voltage is increased, all the emitted electrons will be attracted to the plate. Any further increase in voltage will not increase the current. This is called the saturation point of the electron tube. Triode. A triode is a three-element tube made of a cathode plate and a grid. The triode was developed by Dr. Lee de Forest, In his experiments, de Forest inserted a fine wire mesh between the cathode and the plate of the tube. In doing this, he was able to control the electron flow through the tube. This wire mesh is the grid. The grid in the triode most often has a cylindrical shape. and it surrounds the cathode. The space between the grid wires allows electrons room to pass through to the plate. The grid controls electron flow and is commonly called the control grid. Electron flow is controlled by changes in plate voltage. In the triode, the grid also affects electron flow. For example, a negative grid will repel many electrodes back to the cathode. This limits the number of electrons passing onto the plate. As the grid is made more and more negative, a point is reached where no electrons flow to the plate. This is the cutoff point of the tube. It is the negative voltage amount applied to the control grid that stops control electron flow. Again, it is the negative voltage amount applied to the control grid that stops electron flow. The voltage applied to the control grid is called the bias voltage. A cutoff is called the cutoff bias, or at cutoff it is called the cutoff bias. A triode with both plates and grid voltages is shown in figure 18-5. Notice that the grid bias battery has its negative terminal connected to the grid. In electronic work, these voltages have specific names such as A, B, and C. The A voltage is for the heaters in the tube. The B voltage is for the plate of the tube. The C voltage is for the grid of the tube. Figure 18-6 shows current through an electron tube as the grid bias is changed. The plate voltage is held at a constant value. The curve in this graph is plotted by measuring the value of current at each change of grid voltage. At a grid bias of -2 volts, the current is 8 milliamps. At -6 volts, the current drops to 3 milliamps. Tetrodes. Without neutralization circuits, the triode is limited as an amplifier due to the shunting effect of electrode capacitance at high frequencies. Figure 18-7. To overcome this drawback, another grid is inserted in the triode. This grid is called the screen grid. It is placed between the control grid and the plate. The resulting 4-element tube, cathode, control grid, screen grid, and plate is called a tetrode. Figure 18-8. The screen grid is bypassed to ground externally through a capacitor. The grid is a good screen between the control grid and plate, and this stops the grid plate capacitance, CGP. A DC voltage, slightly less in value than the plate voltage, is applied to the screen grid. The screen grid increases the speed of the electrons passing between cathode and plate. Some electrons are attached to the screen grid, causing a current to flow in the screen circuit. However, most electrons pass through the screen to the plate. High amplification is possible in the tetrode because the control grid is placed very close to the cathode. A decrease or increase in plate voltage has little effect on the plate current due to the isolation effect of the screen grid. Pentodes. While the tetrode has 4 elements, a pentode has 5 elements. In the tetrode, the electrons speed up to strike the plate with force. When this occurs, loosely held electrons on the plate are knocked off into free space. They form a space charge around the plate. This is called the secondary emission. Some of these electrons are drawn to the screen. They detract from useful plate currents through the tube. This effect is more pronounced when the plate's voltage is below screen voltage. To overcome the drawbacks of secondary emission, a third grid is placed in the tube between the screen grid plate and plate. This grid is called the suppressor grid. The tube now has 5 elements: cathode, control grid, screen grid, suppressor grid, and plate. This tube is called a pentode. See figure 18-9. These tubes have high amplification factors and high plate resistance. Inter-electrode capacitance is at minimum. Pentodes were once used as radio frequency or RF amplifiers and as audio power amplifiers. Cathode ray tube, CRT. It is also a vacuum tube. A CRT works in the same manner. Common examples of CRTs include oscilloscope displays and computer monitors. See figure 18-10. The television picture tube is also a type of CRT, referred to figure 18-11. On the left is the cathode and heater. The cathode emits a cloud of electrons. Around the cathode is a metal cylinder. It is closed at one end except for a small hole, an aperture, which controls the flow of electrons into the CRT. It is like the control grid. It also causes emitted electrons to move through the small hole in the shape of a beam. The grid number 2 works at a higher positive potential and is strongly attracted to the negative electrons. This grid causes the electrons to speed up. Grids 3, 4, and 5 further accelerate and focus the electrons. This results in a narrow beam of electrons. Magnetic coil or magnetic deflection coils around the neck of the tube move the electron beams or the electron beam. The electron beam is moved from left to right and top to bottom. The inside of the picture tube is treated with a special type of luminescent material called phosphor. The screen luminescent is a combination of fluorescence, the emission of light during a stimulus, and phosphorescence, the continuation of light after the stimulus has ceased. As the electrons strike the screen, the chemicals glow. The degree of brilliance on the screen is related to the strength of the beam. The picture observed through the glass front of the picture is observed through the glass front of the tube. The inside of the tube bulb contains a conductive coating. External connection to this coating are made from a high voltage power supply. When the electron beam strikes the CRT screen, electrons are knocked off. These electrons are called secondary emission and are collected by the inner coating, completing the circuit. Lesson in safety. Very high dangerous voltages are present at the external connections to this anode, usually from 800 or usually from 8,000 to over 20,000 volts. Use caution when working close to these connections. Work only with one hand to reduce the chance of death from accidental shock. Keep one hand in your pocket. Review questions for section 18.1. Define thermionic emission. It is the release of electrons by heat in some materials. Question 2. The most efficient emitter is the thoriated tungsten oxide coated type. Question 3. The maximum limit of electron flow a vacuum tube will give off, regardless of increases in plate voltages, is the point of saturation. Question 4. The voltage applied to the control grid is the bias voltage. Question 5. High amplification is possible with the C tetrode. Question 6. Secondary emission is a problem connected with what tube? The triode. (18.2) Transistors. On July 1st, 1948, the New York Herald Tribune announced a tiny device that serves nearly all of the functions of a conventional vacuum tube and holds wide promise for radio, telephone, and electronics was demonstrated yesterday by the Bell Telephone Laboratories scientists who developed it. It is known as the transistor. The scientists John Bardeen and Walter Brattain invented the point contact transistor. It had two wires carefully fused on a crystal of germanium. William Shockley followed these inventions by creating the bipolar or junction transistor. These inventions were the beginning of the microelectronics. The transistor provided instant circuit operation and eliminated the warm-up time needed with the vacuum tube circuit. In addition, no large amounts of power were needed with the transistor. The transistor was and still is known for its small size, long life, and light weight. Transistors are key devices in electronics for several reasons. They are able to amplify current. They can create AC signals at desired frequencies. They can also be used as switching devices. This makes them important in computer circuits. The bipolar junction transistor, or BJT, consists of 3 layers of impure semiconductor crystals. This transistor has 2 junctions. There are 2 types of bipolar transistors, NPN and PNP. Blocks and schematic symbols for these are shown in figure 18-12. The NPN bipolar transistor has a thin layer of p-type crystal placed between 2 n-type crystals, figure 18-13. The PNP bipolar transistor has a thin layer of n-type crystals placed between 2 p-type crystals, figure 18-14. In both types, the first crystal is called the emitter. Again, in both types, the first crystal is called the emitter. The center section is called the base. The third crystal is called the collector. In the schematic symbol, notice the direction of the arrow. This indicates whether it is an NPN or PNP transistor. The arrow always points toward the N-type material. This will assist you in determining the proper polarity when making a connection in a circuit. The direction in which the emitter arrow points for a NPN transistor can easily be recalled by reciting "never point in." Figure 18-15 shows biasing diagrams for 5 transistors. Take special note of the fact that the base is not always the same pin location on the transistors. Never assume the proper connections. Always be sure by first checking the transistor part number in a catalog or product specification sheet. The theory of NPN transistor operation is shown in figure 18-16. 2 batteries are used to simplify the operation theory. Most applications require 1 voltage source. The negative terminal of the battery is connected to the N emitter. The positive terminal of the same battery is connected to the P-type base. Therefore, the emitter base circuit is forward biased. In the collector circuit, the N collector is connected to the positive battery terminal. The P base is connected to the negative terminal. The collector base circuit is reverse biased. Electrons enter the emitter from the negative battery source and flow toward the junction, the forward bias has reduced the potential barrier of the first junction. The electrons then combine with the hole carriers in the base to complete the emitter base circuit. Again, the electrons then combine with the hole carriers in the base to complete the emitter base circuit. However, the base is a very thin section of about 0.001 inch. Most of the electrons flow on through to the collector. This electron flow is aided by the low potential barrier of the second PN junction. Approximately 95 to 98% of the current through the transistor is from the emitter to the collector. About 2 to 5% of the current moves between the emitter and the base. A small change in the emitter to base bias voltage causes a somewhat larger change in emitter collector current. Again, a small change in emitter to base bias voltage causes a somewhat larger change in the emitter collector current. This is what allows transistors to be used as amplifiers. The emitter base current change, however, is quite small. A PNP transistor has a P-type material for the emitter and an N-type material for the base, and a P-type material for the collector. See figure 18-17. The power supply or battery must be connected in the opposite way as an NPN transistor. Like the NPN transistor, the emitter to base circuit has forward bias, and the collector to base circuit has reverse bias. In a PNP transistor, most carriers in the emitter to collector are holes. Field effect transistor or FET. The major difference between bipolar junction transistors and field effect transistors or FETs is that the BJT is a current device and the FET is a voltage device. The current through the collector emitter circuit of a BJT is controlled by the amount of current in the base emitter circuit. A FET controls current in the source drain circuit by the amount of potential applied to the gate. There are two types of FETs, the junction field FET or junction field effect transistor or JFET, and the metal oxide semiconductor field effect transistor or MOSFET. First, we will look at the JFET. The construction and symbols for the JFET are shown in figure 18-18. The three main parts of the JFET are the source, drain, and gate. These three parts are similar to the three main parts of a typical bipolar transistor. The source compares to the emitter, the drain compares to the collector, and the gate compares to the base. The gate is diffused into the channel material, and the channel is a path from the source to the drain. The channel through the center of the device can be P or N type material. The current through the device is controlled by the gate potential. See figure 18-19. If a small potential is applied to the gate, a large current through the P channel will exist. If a large potential is applied to the gate, a small current will exist in the channel between the source and the drain. Notice how the potential applied at the gate pinches off the flow of electrical energy. Another type of FET is the MOSFET. It is used extensively in digital circuits and memory circuits. In computers, look at figure 18-20. The MOSFET is similar in construction to the JFET. The difference is that the MOSFET has a very thin film of insulation, silicon dioxide, between the gate and the channel area. Caution, the layer of insulation is so thin that it can easily be damaged by static electricity. Care must be taken when handling MOSFET transistors and devices. The thin layer of high resistance insulation prevents electron flow between the gate and the channel material. The high resistance between the gate and the channel area makes for a very high impedance input device. A high impedance input device is very desirable in circuits such as amplifiers. Also, the channel consisting of the same materials from the source to the drain provides a very low impedance path. A low impedance or low resistance path through the channel is also very desirable for devices such as amplifiers. There are two main types of MOSFET: enhancement mode and depletion mode. In a depletion mode MOSFET, current through the source drain circuit is reduced by gate voltage. In an enhancement mode MOSFET, current through the source drain circuit is increased by the gate voltage. Look closely at the four symbols used for the MOSFET in figure 18-20. The symbols differ for N-type and P-type channel materials and for enhancement mode and depletion mode MOSFETs. Review questions for section 18.2. Name three parts of a bipolar transistor. That's the emitter, the base, and the collector. Question 2. Draw the symbol for an NPN transistor and a PNP transistor and label the parts. In an attempt at that was made toward the top right of the screen by question 2. You can look at the symbols and parts on your text or back, rewind to the beginning of this section 18.2. Question 3. Draw and label the parts for JFET and MOSFET transistor. Likewise, an attempt at this was made toward the top right of the screen again. If you want to look at those, please rewind this recording. Question 4. Draw and label the symbol for an enhanced MOSFET. And that is shown. If not, rewind the tape and watch this recording again. Question 5. Why is the MOSFET so easily damaged by static electricity? That is because of the thin layer of metal oxide between the gate and that same thin gate. Again, is a thin layer of metal oxide between the gate and the channel area. Question 6. What is the difference between a JFET and a MOSFET? And the difference is that a thin film or metal oxide allows for a low impedance source drain circuit path. Question 7. What is the difference between depletion mode and enhancement mode? Depletion mode current is reduced. In the depletion mode, current is reduced by gate voltage. In enhancement mode, current is increased by gate voltage. (18.3) Transistors and amplifiers. An amplifier is an electronic circuit that uses a small input signal to control a larger output signal. In physics, weight can be amplified using levers. A small lever is used to lift a larger weight. In electronics, amplifiers have been used since the early 20th century. Amplification can be accomplished by using vacuum tubes or semiconductor devices such as transistors or integrated circuits. The amount of amplification in a circuit is known as gain. The gain is the ratio between the strength of the outputs. Again, the gain is the ratio between the strength of the outputs, current, voltage, or wattage, and the strength of the inputs, current, voltage, or wattage. Again, figure 18-21. Amplifier circuits can be thought of as a control circuit. A small amount of current or voltage can control a larger amount of voltage or current. These circuits produce outputs that vary or are linear. Amplifier devices such as transistors or ICs can also be used to switch current on or off depending on how they are biased in the circuit. Biasing. For amplifiers to operate properly, they must be correctly biased. Biasing means setting up the correct DC operating voltages between input leads of a transistor. There are two junctions in a transistor. One junction is between the emitter and the base and is called the emitter junction. The other is between the collector and the base and is commonly referred to as the collector junction. For proper transistor operation, energy from the internal power source, battery, or power supply is needed to overcome these junction resistances. As discussed in section 18.2, a bias voltage must exist between emitter and base and of a NPN transistor. Figure 18-22, top of your screen, voltage applied to these elements with the correct polarity will create current flow. This is known as forward bias. Reverse bias is needed in the collector junction of an NPN transistor, figure 18-23. Both forward and reverse bias are needed for the operation of a transistor amplifier. Figure 18-24, bottom of your screen, shows a complete NPN transistor circuit. Notice the forward bias in the emitter junction and the reverse bias in the collector junction. The same type of bias is needed for operation of a PNP transistor amplifier, figure 18-25. The currents for each circuit are labeled. IE is for emitter current, IC is for collector current, and IB is for base current. The emitter junction bias is provided by battery 1 and the collector junction bias is provided by battery 2. Single battery circuit. Two voltage sources have been used in all circuits discussed thus far. One source was used for the forward biasing of the emitter junction, and the other source was used to reverse the biasing of the collector junction. There is no need for two batteries. The amplifier in figure 18-26 uses only one battery. There is no question about the reverse bias of the collector junction. The collector C is connected through RC to the most positive point of the circuit, the positive supply terminal. The most negative point in the circuit is the ground, and it is connected directly to the negative terminal of VCC. Resistors RF and RB form a resistance voltage divider connected directly across VCC. The voltage at the base, B, is less positive than the positive terminal of VCC by the amount of the voltage drop across RF. It is positive in respect to the emitter, E. E is at ground, which is the most negative point in the circuit. By using the proper values of RF and RB, the desired forward bias voltage and current can be established in the emitter junction. The series resistance combination of RF and RB must be large enough so that current drain from the supply battery is small. This ensures long battery life. Methods of bias. The fixed bias method shown in figure 18-27, or the fixed bias method is shown in figure 18-27. Notice that the resistor RB has been omitted. This circuit sets a constant base current. This bias is used for switching circuits. A switch is inserted in the base to control current through the emitter collector. Proper selection of R, RF, and RC sets up the required forward bias and the required forward bias voltages and base current. Again, proper selection of R, RF, and RC sets up the required forward bias voltages and base current. The single battery bias is another common method of biasing transistors, figure 18-28. The emitter biasing is a third method for setting forward bias in the emitter junction, figure 18-29. In this case, the forward bias voltage VEE will set a constant emitter current IE. This produces a voltage drop across RE. RE is chosen to provide the proper forward bias, and RB is the return to complete the emitter circuit. An AC signal applied to the amplifier base will produce a larger AC component in the collector current. This does not upset the emitter bias because a low reactance path around RF is provided by the bypass capacitor C. This circuit ensures a stable operating point for the transistor. A disadvantage of the circuit, however, is the need for two power supplies or batteries. A self-bias schematic is shown in figure 18-30. This circuit differs from the fixed bias method in that bias resistor RF is connected to the collector rather than to VCC. This method provides a more stable operating point than fixed biasing and requires only one power source. A fixed collector current is assumed at some operating point. The collector voltage, VC, will be constant, but it will be lower in value than VCC due to the voltage drop across RC. Any change in IC will also change the values of VC. Since the base is connected to the VC through RE, a certain amount of degeneration will result. What is meant by degeneration? A positive signal at the input of the PNP amplifier makes the base more positive. It decreases its forward bias and increases IC. A reduction in IC means a lesser voltage drop across RC. Collector voltage VC becomes more negative as it reaches the value of negative VCC. This more negative voltage through RF to the base tends to increase forward bias. It also opposes any increase caused by the input signal. In a phase relationship that opposes the input, a signal from the output of a device fed back to the input is called degeneration. The major disadvantage of self-bias is the loss of amplifier gain due to degeneration. Review questions for section 18.3. What is an amplifier? It is an electronic circuit using a small input signal to control a larger output signal. Question 2. Amplifiers can perform two functions. What are they? One is to amplify and two is to switch. Question 3. The process of setting up the correct DC operating voltages between input leads of a transistor is called biasing. Question 4. There are 4 junctions in a transistor. Name them. Amplifier operation. As was described previously, an amplifier is an electronic device that uses a small input signal, voltage, or current to control a larger output signal. Again, as described previously, an amplifier is an electronic device that uses a small input signal, voltage, or current to control a larger output signal. This principle works best when the output load or impedance of the circuit is greater than the input load. Examine figure 18-31. The input is a microphone in the emitter and base control circuit. The output is a loudspeaker connected to the collector and emitter circuit. The load of the loudspeaker is much greater than that of the microphone. The output current in the circuit is about the same as the input current. Recalling Ohm's law, if the input and output currents are about the same and the resistance or load or impedance is 50 times greater in the output than in the input, then the output voltage will be 50 times as great as the input voltage. This process is signal amplification. Refer to figure 18-32. It shows an NPN amplifier circuit with actual component values and specific voltages. The emitter is common to both the input and output circuits. The AC input signal is impressed across the emitter and base of the transistor Q1. The output signal is taken across the collector and emitter of Q1. A capacitor C1 is placed in the input signal to couple or pass the AC input signal to the base for control. A ground is added at a common connection in the battery 1 emitter and the battery 2 circuit. A 0.05 volt peak-to-peak AC input signal is applied across the emitter to base at points Y and Z. As the signal swings positive, the base to emitter forward bias voltage, signal plus bias, will increase.
When the forward bias voltage increases, the base current will also increase, resulting in a smaller resistance across the emitter to collector of transistor Q1. The smaller resistance causes the current in the circuit made of battery 2, R1, and the emitter collector path of Q1 to increase. This increase in current through a fixed value resistor, R1, causes a greater voltage drop across the resistor. See wave number 1. The increase in voltage drop across R1 causes a decrease in voltage across Q1 because they are both in series with the 9-volt battery, battery 2. See wave number 2. Keep in mind the resulting voltage in a series circuit. The total voltage EB2 is equal to the sum of the voltage drops in that series circuit, including the transistor Q1 and the resistor R1. During the negative half of the input signal, the bias voltage on the base is decreased or lowered. As a result, the resistance of the emitter to collector will increase, causing current to be reduced. If the current flowing in the emitter to collector circuit is decreased, current will also decrease in R1 since it is in series with the collector of Q1. If the current through a fixed value resistor R1 is decreased, the voltage drop across it will also decrease. See the negative half of wave number 1. This decrease in voltage across R1 causes an increase in voltage drop across the emitter to collector of Q1 as the sine wave swings positive in wave number 2. In any case, both wave number 1 and wave number 2 must add up to 9 volts. Figure 18-33. Note that wave number 1 and wave number 2 are 180 degrees out of phase. A 0.05 volt signal in the input circuit, emitter to base in Q1, has controlled a 2.5 volt signal in the output, emitter to collector in Q1. This is amplification. Computing gain. There are a number of formulas that can be used to compute types of amplification in transistor amplifier circuits. When the formulas show a triangle or delta symbol, it means the change in a certain value or waveform. Voltage gain. The voltage gain, or AV, is calculated by dividing the change in the output voltage by the change in the input voltage. Formula is shown at the top. The current gain. Current gain, or AI, is calculated by dividing the change in the output current by the change in the input current. The formula is shown right below current gain. Power gain. The power gain, or AP, is calculated like Watt's law. The voltage gain, AV, is multiplied by the current gain, AI. Formula is shown right below. Gain is a ratio and therefore a dimensionless number. Gain simply tells how much a signal has been amplified. The value is a number like 100, meaning the voltage gain is 100 times in the output than in the input. Decibels. A decibel, written as dB, is a unit of relative measurement. When a measurement is definitive, it has a definite weight, size, volume, etc. When a measurement is relative, it must be compared to a similar known object. Compared to different shades of blue, such as blue sky and the blue water, there is no definite measurement. as to just how much or how blue the sky or how blue the water is. However, we can compare the shades of the sky and the water to determine which is more blue. The decibel was developed as a way to measure the relativity of sound or to compare the level of sound to another. To compare one level of sound to another. In the field of electronics, audio systems are expressed in decibels. Many times amplifiers are also classified in terms of decibels. Instead of having a definite inputs, the outputs of the system or amplifier is expressed in decibels. This is a way of saying that the output is 10, 100, or 1000 times 1000 or more times greater than the inputs. A decibel rating gives relative power level and not an actual power rating. To have a clear understanding of the decibel rating, we must understand logarithm or logarithms of numbers. It is not within the scope of this textbook, however, to cover logarithm tables. Review questions for section 18.4. If number 1, if the output AC signal voltage is 200 millivolts and the input AC signal is 10 millivolts, what is the voltage gain? The formula is shown on top. Amount of change or delta outs and the amount of change delta in. And in this case, we have 200 millivolts divided by 10 millivolts, which equals to 20 millivolts. That is the amount of change that we have. Question 2. Output AC current is 750 microamps and AC input current is 150 microamps. Find the current gain. Formula is shown. Delta I outs divided by delta I in. In this case, 750 microamps divided 150 microamps gives us a total of 5 microamps for the answer. Question 3. Compute the power gain when the output voltage gain is 175 and the current gain is 5. So we use the formula delta V or voltage times delta I or current. In this case 175 times 5 or 875. (18.5) Transistor circuit configurations. The transistor can be connected in 3 circuit configurations. The configuration used depends on the element that is common to both input and output circuits. Usually the common element is at ground potential. In figure 18-34, a common base CB amplifier circuit is shown. The AC input signal between emitter and base will vary the forward bias by alternately adding to and subtracting from the fixed bias. The increase and decrease in current in the emitter controller circuit produces the amplified voltage across RL. The input signal and the output signal are in phase. There is no signal inversion. In figure 18-35, right side of the screen, a common emitter or CE circuit is drawn. This is the most common transistor circuit. In the common emitter circuit, a positive input signal makes the base more positive and or less negative with respect to the emitter, thus reducing the forward bias of the circuit. A negative input signal makes the base more negative and increase the forward bias. As a result, the voltage across RL in the output circuit is 180 degrees out of phase. In the common emitter circuit, the gain is the ratio between the change in collector current and the change in base current. The current is represented by the Greek letter B or beta. The formula is shown at the bottom of the right side of the screen. In this equation, beta equals current gain in common emitter circuits. Delta IC equals the change in collector current, and delta IB equals the change in base current. VC, or collector voltage, is held constant. Note: in transistor circuits, voltage is represented by the capital V instead of E as used elsewhere. Figure 18-36 shows a common collector, or CC, circuit. The signal is applied between the base and collector. The output is taken from the collector emitter circuit. It has a very high input impedance and low output impedance. This circuit is useful as an impedance matching circuit. The input and output signals are in phase. The voltage gain in this circuit must always be less than 1. Figure 18-37 shows common input and output impedance values for common base, CB, common emitter, CE, and common collector, CC, amplifier circuits. Figure 18-38, bottom of the screen, shows the phase relationships between the input signal and output signals in CB, CE, and CC amplifiers. DC load line analysis. A transistor load line analysis is a graphic display that plots the maximum current value of the collector against the maximum voltage across the emitter collector. This graph is used to predict transistor characteristics under changing load conditions correlated to a particular voltage drop across the emitter collector. This graph is only an approximation. It does not take into consideration some influences that can affect transistor performance, such as temperature and individual transistor characteristics. Look at figure 18-39 on your screen now. The bottom line of the graph represents voltage across the emitter collector of the transistor. The maximum voltage is equal to the supply voltage. See figure 18-40. When a transistor is not conducting, it is said to be at cutoff. In this condition, it is similar to an open switch. The full applied voltage can be read across the emitter collector circuit. Again, take a look back at figure 18-39 and compare it to figure 18-40. See where the top of the slope line connects to the vertical axis, which indicates the current values in milliamps. This point represents the maximum current through the collector and is based on the current through the load resistor. Using Ohm's law, the collector current can be determined by dividing the supply voltage by the load resistor value in ohms. Again, using Ohm's law, the collector current can be determined by dividing the supply voltage by the load resistor value in ohms. Since the load resistor is connected in series to the collector, the current values will be the same. Maximum current through the collector is the saturation point of the transistor. Looking at figure 18-41, you will see that the quiescent point, or Q point, located at approximately the midpoint of the sloping line, The Q point is where the optimum performance characteristics for the transistor are displayed. For many amplifiers, the Q point will be approximately one half of the supply voltage. Rather than a maximum gain, a small gain in an amplifier results in a better sound quality from the amplifier. If the gain is too high, the transistor will be driven both into saturation and cutoff, which results in a distortion of the amplified signal. Compare figure 18-41 to figure 18-42, which is now shown on the screen. A small gain results in a near perfect replica of the input signal. Again, compare figure 18-41 and 18-42. A small gain results in a near perfect replica of the input signal. A large gain or excessive amplification of an input signal results in distortion. The amplified signal distortion is caused by the amplified signal exceeding the saturation and cutoff point, thus cropping off the top and bottom of the signal wave. The same thing happens to an audio signal that is amplified too much. A multi-stage amplifier designed for small gains of 7 to 10 has far better sound quality than an amplifier with only a few transistors with large gains of say 50. This is one reason for the large variation in prices for amplifier systems. The amplifier with many stages will undoubtedly cost more and sound better. Classes of amplifiers. Amplifiers are classified according to their bias current. The bias current determines the output waveform compared to the input waveform. Class A. The Class A amplifier is biased so that an output signal is produced for 360 degrees of the input signal cycle. See figure 18-43. Current flows at all times. The output of a Class A amplifier is an amplified copy of the input signal. Its efficiency is low. This class is widely used in high fidelity sound systems. Class B. A Class B amplifier is biased so that an output signal is reproduced during 180 degrees of input signal. The Class B amplifier is biased close to cutoff. See figure 18-44. Since collector current flows only one half of the time, this amplifier has medium efficiency. It is similar to a half-wave rectifier. The output is distorted. Two amplifiers operated in a push-pull configuration can restore both halves of the signal in the output. The push-pull circuit has increased efficiency and greater power output. It will be used in many audio amplifiers as the final output stage. Push-pull coupling is covered in detail in section 18.6. Finally, Class C. A Class C amplifier is biased so that less than 180 degrees of output signal is produced during 360 degrees of input signal. This class finds limited use in transistor circuits. Thermal considerations. Transistors are easily overheated. As operating temperature increases, there is greater thermal activity in the crystalline structure and a decrease in resistance. Repeated resistance decrease and current increase can cause destruction of the transistor. This condition is called thermal runaway. There are a few methods that prevent thermal damage to a transistor. One way of reducing overheating is through the use of special circuits. See figure 18-45, the common emitter amplifier has a stabilizing resistor R3. An increase in current makes the emitter end of R3 more positive with respect to ground. The forward bias of the emitter base circuit decreases. This decrease acts as a limiter to current increase resulting from thermal runaway. C3 is a bias C3 is a bypass capacitor that prevents degeneration and loss of gain. Again, C3 is a bypass capacitor that prevents degeneration and loss of gain. Another method of preventing thermal overheating is through the use of heat sinks. Heat sinks are large pieces of metal, usually with thin fins, that absorb and disperse heat that is generated in a transistor. See figure 18-46. Transistor precautions. Transistors are delicate electronic components. The following are a number of precautions you should take to protect transistors from damage. First, do not remove or replace transistors in circuits. When the power is on, surge currents can destroy the transistors. Number two, be very careful with close connections such as those found in miniature transistor circuits. A brief short circuit can burn out a transistor. Number three, when measuring resistances in a transistor circuit, remember that the ohm meter contains a battery. If it is improperly applied, it will burn out a transistor. It is also important to observe the correct polarity when measuring ohms for accurate readings. And finally, number four, soldering the leads of transistors is a skill which must be developed. Heat will destroy the transistor. When soldering a transistor lead, grasp the lead between the transistor and the connection to be soldered with a pair of long nose pliers. These pliers will act as a heat sink and absorb the heat from the soldering. Use a pencil type soldering iron of no more than 25 watts. Review questions for section 18.5. Name three types of transistors configurations. First is the common base, second is the common emitter, and the third is the common collector. Question 2. This class of amplifier has an output signal that is an amplified copy of the input signal. The answer is class A. Question 3. This class of amplifier has an output wave 180 degrees out of phase with the input signal. The answer is class B. Question 4. The total effect of uncontrolled decreasing resistance and increasing current in a transistor circuit is called thermal runaway. Finally, question 5. What is a heatsink? It is a metal structure that allows for heat dissipation. (18.6) Coupling amplifiers. Transistor stages can be connected in series to produce the desired amplification. Connecting these stages in series is called cascading. The key challenge of cascading is matching the high impedance outputs of one transistor to the low input impedance of the next transistor without severe loss in gain. Transistor stages can be connected using one of the following four primary methods. Shown on the screen are 1. Transformer coupling, 2. RC coupling, 3. Direct coupling, and 4. Push-pull coupling. Transformer coupling. The circuit in figure 18-47 top of the screen shows two stages of transistor amplifier stages coupled with a transformer. Transistor Q1 has an output impedance of 20 k ohms, and Q2 has an input impedance of 1 k ohm. A severe mismatch and loss of gain results when they are directly connected. A transformer can match these impedances. In this case, a step-down transformer is required. A low secondary voltage means a higher secondary current. This condition is acceptable for transistors because they are current operated. Many special sub-ouncer and sub-ouncer transformers have been developed for this purpose. See figure 18-48, bottom of the screen. The purpose of capacitor C in the transformer coupling circuit in figure 18-47 up top is to block the DC bias voltage of the transistor from ground. Note that if C is left out, the transistor base will be grounded directly through the transformer secondary. The major drawback of transformer coupling, besides the cost, is the poor frequency response of transformers. They tend to saturate at high audio frequencies. At radio frequencies, inductance and winding capacitance present problems. A type of transformer coupling that avoids this problem uses a tapped transformer. These taps can be medium, low, and high impedance points. Good impedance matching can be attained with taps, as well as good coupling and gain. Study the circuit shown on the screen, 1849. For radio frequency amplifier circuits, both the transformer, primary and secondary windings can be tuned by variable capacitors for frequency choice. There's one other key point about the transformer. The primary impedance of the transformer acts as a collector load for the transistor. This impedance only appears under signal conditions. The load is XL of primary. Again, the load is XL of primary. That is inductive reactance. From the DC point of view, the only load is the ohmic resistance of the wire used to wind the transformer primary. This information will be helpful when designing a power amplifier. RC coupling. A simple and less costly method of coupling transistor amplifier stages is to use resistor capacitor or RC coupling. See figure 18-50. In part A of figure 18-50, a capacitor C charges to 10 volts. Only during the charging of C will a current cause a voltage across R. Again, only during the charging of C will a current will cause a voltage to appear across R. After C is charged, VC will equal 10 volts and VR will equal 0. If the source voltage is charged, if the voltage source is changed to 12 volts, again, if the source voltage is changed to 12 volts, VC will also increase to 12 volts. Part B of figure 1850. The charging current will produce a brief 2-volt pulse across R in the polarity shown. If the source voltage is changed to 8 volts, C will discharge to 8 volts. Part C of figure 18-50. The discharge current will produce a brief voltage pulse across R in the polarity shown. In part D of figure 18-50, both DC and AC voltages are connected to the RC circuit. The AC signal causes the total voltage to vary between 8 and 12 volts. Therefore, C charges and discharges at the AC generator frequency. The voltages, or the voltage across R, rises and falls at the same frequency as the generator voltage. Again, the voltage across R rises and falls at the same frequency as the generator voltage. Look at figure 18-51. The input signal varies around a DC level of 10 volts, but the output signal varies around the 0 volt level. The DC component has been removed. A capacitor blocks DC. Again, a capacitor blocks DC. A capacitor used to block DC is called a blocking capacitor. From a mathematical viewpoint, C and R in series form an AC voltage divider, figure 18-52. Again, C and R in series form an AC divider. Voltage division depends on the reactance of XC. That's the capacitive reactance. At the frequency of the signal, again, voltage division depends on the reactance of XC at the frequency of the signal. Voltage output across R is a key consideration when the greatest amount of AC voltage must appear across R. With a 1000 Hz frequency signal and a C value of 0.01 microfarads, we get the following formula. Mathematically, XC equals to 1 over or divided by 2 pi frequency and capacitance. That is the formula. In this case, we have 1 divided by 6.28 times 10 to the third power hertz times 1 times 10 to the negative 8 power farads, and we ultimately get 16,000 ohms. That's the capacitive reactance. If the value of R is 10 or more times greater than XC, then most of the voltage will appear across R, assuming R equals 160 k ohms. That is 16,000 k ohms. Excuse me, that's 16,000 ohms. Then looking at the formulas, VR equals to R divided by R plus XC times Vn. Plug in the values. 1.6 times 10 to the 5th power ohms divided by 1.6 times 10 to the 5th power ohms in parentheses plus 1.6 times 10 to the 4th power ohms in parentheses. We ultimately get, as you can see on the bottom of the screen, 9.1 volts. It seems that almost all of the voltage appears across R. Less than a volt has been lost as signal output. If R were made larger, then even more of that total output would be developed across R. Looking at the two-stage amplifier using transistors in figure 18-53, consider the signal voltage at the collector of Q1. There is more than one path for the voltage, and it will always take the easiest path. It can go through RC or through the coupling network that is in parallel. If the network impedance is higher than RC, signal currents will go through RC instead of the next stage. Therefore, the coupling capacitors used in transistor circuits must have values in the range of 8 to 10 microfarads. To prove the point, assume Q2 input impedance is 500 ohms. XC would need to be 50 ohms or less at 1000 Hz frequency. This is shown in the formula. on the screen, where C equals 1 divided by 2 pi frequency times XC, which in this case, plug in the values 1 divided by 6.28 times 10 to the third power hertz times 50 ohms, which gives us more or less 3.2 microfarads. At lower amplified frequencies, XC would be higher. A capacitor of 8 to 10 microfarads would be required to prevent loss of amplifier gain. Note also that in figure 18-53 that RF and RB are in parallel with the emitter base circuit. These resistor values must be high enough so that the signal will not be bypassed around the emitter junction. The values of RB and RF are based on the required bias and stability of the circuit. Current drain from the source is also considered. Transistor circuit design can become quite complex and is often a matter of give and take. Compare the outputs and input impedances of the transistors and in the CE configuration. The input can be in the 500 to 1.5 kilo ohm range. The output impedance is in the 30 kilo ohm to 50 kilo ohm range. This is a severe mismatch. With the RC coupling, the loss of power gain caused by the mismatch must be accepted. When cost is a factor, it may be cheaper to add another transistor stage. This addition will offset the loss of power. This addition will offset the loss due to the mismatch and is less costly than purchasing a transformer for interstage matching.
Direct coupling. In many circuits, very low frequency signals must be amplified, or perhaps any change of bias must be retained. Current is amplified by the direct coupled circuit. Push-pull coupling. Two transistors joined in parallel in a figure 18-57 on Q1 conductions for section 18.6 shown by arrows. Connecting amplifier stages in series is called a transformer. Can be used to couple amplifier stages together, as well as match input and output impedances. Thyristors are a special family of semiconductor devices. Name two disadvantages of transformer coupling semiconductor devices that are used as switches. Poor frequency response. Two common thyristor devices are the SCR and the triac, referred to figure 18-53. Q1 is connected to Q2. The silicon-controlled rectifier, or SCR, is used in many DC motor control applications. If the collector of one amplifier is hooked to the base of the next amplifier with no other components in between, the coupling method is called direct coupling. Question 6. Connecting two amplifier stages in parallel is referred to as push-pull coupling. The gate is connected to some type of triggering circuitry that allows for control of the conduction of the SDR. The SCR, again, the gate is connected to some type of triggering circuitry that allows for control of the conduction of the SCR. The SCR is capable of handling large DC current values, figure 18-59. The triac. The triac is similar to the SCR in construction and is capable of handling large AC current values. Figure 18-60 shows that the triac is constructed of 5 layers of semiconductor material such as NP and PN. The additional layer of semiconductor material allows the triac to control AC current. The triac is used extensively as a light dimmer control on AC circuits and in some AC motor applications such as hand drills. Figure 18-61 shows the schematic symbol for the triac. The triac has 3 main leads, anode 1, the gate, and anode 2. The triac is designed as 2 SCRs facing opposite directions. It operates on the same principle as the SCR to control AC current. And now some review questions for section 18.7. This is the last section for this chapter. Question 1. What are the 3 main parts of an SCR? That is the anode, the cathode, and the gate. Question 2. How must an ACR be turned off? And that is, it should be shut off. The 1. Shut off voltage at the anode, and 2. Reverse voltage at the anode, and 3. Substantially reduce voltage. Those are the 3 ways. Question 3. What are the 3 main parts of a triac? That is the anode, the gate, and the anode. Again, there's anode 1, gate, and the anode 2. Those are the 3 main parts of the triac. Question 4. How would you use a SCR or a triac to control a 100 watt 120 VAC lamp? The question again is, would you use a SCR or a triac to control a 100 watt 120 volts AC lamp? And you would have to use a triac since it is the only device that can handle AC of the 2. And now the summary for chapter 18. 1. The 3 generations of electronic devices are the vacuum tube, developed in the late 19th century and discovered in 1904 as a rectifier device; the transistor, invented in 1948, and the integrated circuit, or IC, invented in 1958. 2. Vacuum tubes have been replaced in large part by the use of transistors and integrated circuits. 3. The vacuum tube still finds some special uses, such as in cathode ray tubes, CRTs. Cathode ray tubes are special vacuum tubes used in televisions, oscilloscopes, and computer screens, among other places. Question 4. Vacuum tubes operate on the principle that certain metals and metal oxides give up free electrons when heated. This process is known as thermionic emission. 5. The transistor is a semiconductor device capable of application, oscillation, and switching. Again, that is amplification, oscillation, and switching. The 3 basic leads of a transistor are the emitter, the base, and the collector. 7. Bias is the voltage difference between 2 input elements of a circuit. 8. In normal operation of a transistor amplifier, the input elements are usually forward biased, while the output elements are reverse biased. 9. The 3 basic leads of a FET are the source, the drain, and the gate. 10. FETs are voltage control devices, while transistors are current control devices. 11. There are two types of FETs, the JFET and the MOSFET. 12. The MOSFET can be operated in two modes, enhancement and depletion. 13. Amplifiers are electronic circuits that control output signals with input signals. 14. Formulas to compute gain are the following, shown at the top of your screen. 15. Three transistor circuit configurations are common base amplifier, or CB, common emitter amplifier, or CE, and common collector amplifier, or CC. 16. Amplifiers can be classified according to their bias current. Some classes are A, B, and C. 17. Transistors and other semiconductor materials are sensitive to heat. Heat sinks protect transistors and other semiconductor devices from excessive heat. 18. Some important methods of coupling amplifiers are the transformer coupling, the RC coupling, the direct coupling, and push-pull coupling. 19. Thyristors are special semiconductor devices capable of handling large currents. Two common thyristors are the SCR and the triac. Again, the SCR is the silicon controlled rectifier. Test your knowledge questions for this chapter, chapter 18. Some of the answers are either right by the question or on the right side of the screen, according to their respective question number. Question 1. Name 3 disadvantages of the vacuum tube when compared to the transistor. And that is the power efficiency, the size, and weight. I have some other answers that I put on my own, which are speed, durability, the energy efficiency, the size, etc. Some of them the same as the answers for the text, from the text. Question 2. Draw and label the symbols for a diode, triode, tetrode, and pentode. Those are drawn on the right side of the screen. Question 2. Question 3. Determine the approximate voltage needed by the following tubes. A 5Y3. The answer for that one is plus or minus 5 volts. For the B, 12AX7, plus or minus 12 volts. C and 35 is 35W4, plus or minus 35 volts. Remember that the voltage is denoted by the first 1 or 2 digits of the part number. Question 4. What is the purpose of the grid in a triode? And it is to control electron flow. Through a wire mesh to a control, which is the control grid, which is controlled by change in plate voltage. So the purpose is to control electron flow or current. 5. In what tube is the suppressor grid found? And that is in the pentode. 6. Draw a NPN transistor symbol and label the emitter, base, and the collector. You can see that on the right side of the screen again, number 6. 7. How do the voltage connections from the source differ between NPN and PNP transistor? And the answer is again on the right side of the screen. On an NPN, the first crystal, negative must be, or N must be a negative voltage input to be forward bias, and the third crystal a positive input to be a reverse biased. The opposite must occur in a PNP transistor. Question 8. Which part of an NPN transistor common emitter configuration has the largest amount of current present during amplification? And the answer for that is the emitter. Question 9. A field effect transistor is a voltage controlled device. Question 10. Which parts of a NPN transistor, common emitter configuration, or CE configuration, normally has the least current present during normal operation? Again, which part of the NPN transistor in CE configuration normally has the least current present during normal operation? That is the base. Question 11. Care must be taken to prevent static electricity from coming into contact with a MOSFET. Question 12. The arrow pointing toward the gate in the MOSFET symbol means that the gate is connected to a negative polarity. Question 13. What are the two operating modes of the MOSFET? That is depletion and enhancement. Question 14. An amplifier is all of the above, which is a control device, uses a small input signal to control a larger output signal, and produces outputs that are linear. All of these are true for an amplifier. 15. Define gain. And gain is the ratio between the strength of outputs and inputs of an amplifier. 16. Name 3 methods of transistor bias and draw the schematic for each. And 16 is seen on the right side of the screen again. Forward bias for the emitter junction, NPN, is shown. The reverse bias for the collector junction in NPN is also shown. That's bottom right in your screen. And the forward and reverse bias in NPN circuit is shown top right of your screen. Question 17, write the formula for computing voltage gain. That is shown on the right side of the screen, number 17. 18, write the formula for computing current gain. Again, shown on the right side of the screen, number 18. Write the formula for computing power gain. That's question number 19 and is shown in number 19 on the right side of the screen again. Question 20. How is gain for a common emitter circuit computed? And the formula is shown, or beta equals delta IC divided by delta IB. Question 21. The input and outputs waveforms of a common collector amplifier? And the answer is are A in phase. Question 22. Draw a direct coupled amplifier using two NPN transistors, and that is shown on the right side of the screen toward the bottom. Number 22. And finally, question 23. Last question is what precautions should be observed in the use of and servicing of transistor circuits? And that is heat, static electricity, polarity, and voltage must be observed. Here are some of the projects for chapter 18. It is a massive chapter, quite loaded and somewhat complicated, so I would follow along some of the projects, go back, review, understand, make sure you understand the major concepts described here, and especially some of the new language and some of the new definitions that you encountered throughout the chapter, but most importantly, the concepts of some of the items in the chapter, such as the operation of vacuum tubes must be understood, how diodes work, the different types of diodes, different types of vacuum tubes, which will help you understand the transition to the newer technologies such as transistors, understand how what transistors are, how transistors work, the different types of transistors, the different parts for each type of transistor. Make sure you understand what biasing is. Understand very clearly amplifiers and their operation. You should understand what gain is in amplifiers. How do you compute gain? You should understand very clearly a transistor, the different transistor circuit configurations, which are a few. They have, for example, the common base CB configuration, common emitter CE configuration, common collector CC configuration. You should understand what those are and what the difference are in between them, what their purposes are for different configurations. You should understand different classes of amplifiers, class A, B, and C. You should also understand some of the precautions needed for some of the devices discussed, such as for heat, voltage, polarity, and static electricity, how those could damage transistors and other devices. Coupling amplifiers, you should know what those are or understand, and basically also know about their stages, know what cascading means for coupling amplifiers, understand what transformer and RC coupling is and what their purpose is and where they are used. You should understand about direct coupling and pull coupling. And finally, you should understand the concepts and the descriptions for thyristors, what thyristors are, and the different types of thyristors, which are two: the SCR, the silicon controlled rectifier, and the triac. One of them is used for DC circuits, the other ones the other one for AC. You should know which one's used for which type of current. And that pretty much wraps up this very massive chapter, and chapter full of information. So make sure you go back, understand each and every concept. If you have to go back to the previous chapter, do so, which is the introduction to semiconductors and power supplies, which is basically built up on this chapter and allows you to understand this chapter a lot better. And of course, all of the chapters before that. This is a sidebar for X-rays. Quick topic that's quite interesting. X-rays were accidentally discovered in 1895 by German physicist Wilhelm K. Röntgen. Röntgen called the phenomena X radiation because at the time its nature was completely unknown. It is now known that X-rays are a kind of electromagnetic radiation that also includes visible light, radio waves, and gamma rays. Like visible light, X-rays travel in straight lines at the speed of light. They also darken photographic film in much the same way. X-rays differ from visible light in the terms of wavelength. The X-ray is very high in the electromagnetic spectrum of waves. The useful range of medical radiography is relatively short, with wavelengths of approximately 0.01 to 0.05 nanometers. The short wavelengths are less easily absorbed and are therefore more penetrating. The construction of the X-ray tube is similar to the vacuum tubes studied in this chapter. The two main parts of an X-ray tube are the anode, positive electrode, and the cathode, the negative electrode. When an X-ray tube is in operation, the cathode heats up and emits a stream of electrons. This is referred to as thermionic emission. The focusing cup directs the stream of electrons toward the anode surface. The anode has a high positive charge on its surface, which attracts the free electrons. The high voltage causes the electrons to strike the anode with such force that X-rays are produced. These rays reflect off the anode and pass through a clear window on the side of the tube. The X-rays then pass through the target area and are received on a photographic plate. The light and dark areas appear on the plate in direct relationship to the density of the material through which they are traveling. Bones are quite dense and appear as white areas on an X-ray plate. The body's flesh has a lower density and allows for more of the X-ray to pass through. When the electrons strike the surface of the anode, a great deal of heat is generated and the surface can become pitted. X-ray machines using a rotating anode are more powerful and have a longer life. The anode rotates at speeds of up to 10,000 RPM, allowing more surface area to be struck by the thermoic or thermionic cloud, which in turn produces less heat. Fluoroscopy is another diagnostic medical procedure that uses X-ray. Physicians can use this procedure to view organs and to observe such medical procedures as the insertion of a catheter or the removal of foreign objects. Before some fluoroscopic examinations, a patient drinks a liquid containing a barium compound. Barium strongly absorbs X-rays, so the organs show up more clearly. X-rays are converted into visible images and recorded by a television camera. Physicians view the image on a monitor to convert it to a still picture. Powerful X-rays can be produced to penetrate even steel and concrete. X-rays are used in the construction industry to inspect structural members and welded seams. Archaeologists use X-ray techniques to collect data on such items as mummies. Airport security systems use X-rays to examine luggage and passengers for illegal or dangerous items. And this is the end of this chapter, which is again introduction to semiconductors and power supplies. That's chapter 17, and chapter 18, which is tubes, transistors, and amplifiers. Again, a very full and loaded chapter. Make sure you go back and review if needed before moving on. Congratulations, you have earned this electronics course rank. Thank you very much.